In this section, we will introduce some basic concepts in probability. The word probability or its equivalent appears frequently in our daily conversation or reading. For example, when tossing a coin, one will get a head with 50 to 50 chance. Here, 50 to 50 essentially means that the probability of head is 0.5. In the second example, a student is 90% sure that he will pass an exam. This 90% is also indicate the probability. Before introducing the rigorous definition of probability in mathematics, let us check how to understand this word. These two examples essentially illustrate two different typical interpretations of probability. In the first one, the example of tossing a coin, the probability can be understood as the proportion over long run repeating. It means that 50% is the proportion of heads when tossing the coin many times. In the second example, the probability 90% indicates just the level of personal belief. It is simply a subjective value. In this course, we mainly interpret probability in terms of proportion. Probability is a generalization of concept of proportion. When tossing a balanced coin, the probability of head is 0.5. It indicates that when tossing a coin 100 times, we expect to get about 50 heads. When tossing a coin 1000 times, we expect to get about 500 heads. When tossing a coin 10,000 times, we expect to get 5,000 heads. Those 50 heads, 500 heads, 5,000 heads are just expectations. The actual number of heads may show some variation in practice. For example, the two plots demonstrate two attempts of tossing a coin 100 times. The horizontal axis is the number of tosses. The vertical axis is the proportion of heads. We can see that in the beginning, the proportion of heads can be quite different from 0.5. However, as the number of tosses increases, the proportion of heads tend to get closer and closer to 0.5. This is exactly the meaning of probability. When we toss a balanced coin a limited number of times, the proportion of heads shows a large variation. However, the proportion will become stable when the number of tosses is large enough. We will formally define the concept of probability. Before that, we need to define some other concepts. An experiment is an action whose outcome cannot be predicted with certainty. For example, tossing a coin is an example. An outcome is one possible result when performing an experiment. When tossing a coin, the outcome may be a head or may be a tail. The sample space is the collection of all possible outcomes for an experiment. For tossing a coin, the sample space includes two possible outcomes, head or tail. When finding the sample space, make sure to include all possible outcomes, no matter how likely or unlikely they may occur. An event is a collection of outcomes or a subset of the sample space. An event occurs if and only if the outcome of the experiment is a member of the element. The concept events is important. Later, we will see that the probability is defined as a function of events. We may say the probability of an event, but it is incorrect to say the probability of an outcome. Let's consider this example. Toss a balanced die. The experiment is to toss a balanced die once. There are 6 possible outcomes for this experiment, namely 1, 2, 3, 4, 5, 6. The sample space, therefore, contains all the 6 outcomes. Here, we want to emphasize that a set is presented by the curved bracket, where the elements in the set are listed in the curved bracket. Let us define some events. Usually, we will use a letter to denote an event. The first event, event A, contains only one member, which is 4. The second event, B, means outcomes that are even numbers, which include 3 outcomes, 2, 4, and 6. The third event, C, is outcomes larger than 4, which are 5 and 6. Hence, C contains 2 elements. We can see that after identifying the sample space, it is easy to identify an event. We simply find all outcomes that meet the requirement for that event. If we toss the die once and the outcome is 4, we may say that event A occurs because 4 is a member of event A. We may also say that event B occurs because 4 is also a member of B. We will say that event C does not occur because C does not contain 4. If we toss the die once and the outcome is 6, we may say that event A does not occur because 6 is not a member of A. We will say that event B and C occur because they include 6 as a member. In this event, we will toss a balanced coin twice. Notice that one possible outcome will contain the result of the first toss and also the result of the second toss. Here, there are 4 possible outcomes, HH, HT, TH, and TT. We will use letter H to denote head and T for tail. The sample space contains 4 elements. Let us define some events. For the first event A, it contains the outcomes with exactly one head. We check the sample space to see which outcomes have exactly one head or H. There are 2 possible outcomes, HT and TH. So event A contains 2 outcomes. The second event B includes the outcomes whose first toss is a head. It has 2 elements, HH and HT. When toss a coin twice, we get a tail first and then a head. We may say that the event A occurs but event B does not occur because A includes TH and B does not include TH. When toss a coin twice, we get a head first and then a tail. We may say that both events A and B occur because both of them contains HT. Let's see how to calculate the probability when outcomes occur equally likely. Suppose that an experiment has n possible outcomes, or equally likely. The probability of an event is exactly the number of outcomes in the event divided by the total number of possible outcomes of this experiment. The steps list how to calculate the probability for such a case. Firstly, identify all the possible outcomes of the experiment. Suppose that this number is n. Then identify all the outcomes in this event. Suppose that this number is f. The probability of the event is therefore f divided by n. Consider the experiment of tossing a pair of dice. Find the probability that the sum of the dice is 11. Then find the probability that doubles are rolled. For double, we mean that both dice come up the same number. This is a typical question in probability. For such a question, we first need to identify the sample space, or all the possible outcomes. One die has 6 possible outcomes. A pair of dice have 36 possible outcomes. The 36 possible outcomes are listed in the slide. We use red and black color to indicate two dice. Clearly, each outcome occurs equally likely. We can apply the formula we just discussed. To find a probability, we need to find how many outcomes in each event, then divide this number by 36. We work out the probability one by one. In the first question, event A means the number of dice is 11. For all 36 outcomes in the sample space, we calculate the sum of the dice for each outcome. Identify those with a sum of 11. There are only two possible outcomes, 5, 6 and 6, 5. The event A contains two possible outcomes. Hence, the probability of A is 2 over 36, or approximately 0.056. In the second question, event B means doubles are rolled. There are only 6 possible values for each die. Therefore, there are exactly 6 possible doubles. Event B contains 6 outcomes. The probability of B is 6 over 36, or approximately 0.167. As a summary, when two balanced dice are rolled, there is a 5.6% chance of a sum of 11, and there is a 16.7% chance of doubles. Let's summarize some properties of probability. The probability of an event is always a value between 0 and 1, inclusive. No probability can be negative, and no probability can be larger than 1. The probability of an event that cannot occur is 0. Such an event is called an impossible event. The empty set is an impossible event. Notice that an empty set means a set contains no element. For example, when rolling two balanced dice, define the event as the outcomes whose sum is 1. The smallest possible value of a die is 1. Therefore, the smallest possible sum is 2. It is impossible that the sum is 1. Hence, the event is an empty set, and its probability is 0. The probability of an event that must occur is 1. Such an event is called a certain event or sure event. The sample space contains all possible outcomes. It is also an event by definition. The probability of the sample space is 1. For example, when rolling two balanced dice, define the event as the outcomes with sum being 12 or less. The largest possible value of a die is 6. Therefore, the largest possible sum is 12. This event contains all possible outcomes. So this event is exactly the sample space. Its probability is 1. In the last, we want to emphasize that the probability of an event is the proportion of time it occurs in a large number of repetitions of the experiment. A probability near 0 means that the event is very unlikely to occur. A probability near 1 means that the event is quite likely to occur. The larger the probability is, the more likely the event occurs. This interpretation makes sense in many applications, such as tossing a coin or dice. However, this interpretation may not be natural for some scenarios. For example, we may say that the probability that Mark will pass the final exam is 0.9. We may try to explain this probability in one of the following ways. First, we may let Mark take many exams with the same level of difficulty. He can pass 90% of them. This 90% is a proportion and also the meaning of probability in the sentence. Secondly, suppose we have the power of rewinding the time as in many sci-fi movies. We erase Mark's memory and let him take exams repeatedly. Mark can pass 90% of the time. As we mentioned in the very beginning, a probability can be interpreted as personal belief. This interpretation may be more natural in this example. In some books, this interpretation of probability is adopted. However, it will lead to a totally different set of statistical methods. They are called Bayesian statistics. We will not discuss them in this course. In this course, we only discuss frequentist statistical methods.